Hello and welcome back to Amazing World Facts, the place where we explore the deepest mysteries of our universe. Today's question is one that has fascinated human imagination for centuries. Can time travel ever be possible? From H.G. Wells to Back to the Future, time machines have filled our dreams. But is there any truth behind them? Could we someday step into a machine, twist a dial, and find ourselves in 1500 AD or 300 years into the future? Or is time travel forever confined to the realm of fiction? In this video, we'll take you on a journey through physics, relativity, quantum mechanics, paradoxes, and the latest cutting-edge research to ask whether time travel could ever be more than science fiction. Buckle up because we're entering the loops of space-time. First, a clarification. When physicists talk about time travel, they usually mean traveling to a different point in time than your own. There are two broad categories. One, forward time travel, going into the future faster than normal. Two, backward time travel, going into the past. You might say, but we already do time travel. Every second moves us 1 second to the future. That's true? That's true, and in fact, relativity shows even more. Under the right conditions, you can accelerate into the future faster, relative to someone left behind. As Scientific American says, time traveling to the near future is easy, according to Einstein's special theory of relativity. NASA also notes that under strong gravitational fields or high velocities, clocks run slower or faster. You experience time at a different rate. So, forward time travel is well established scientifically. It's not magic, it's physics. But the real challenge, and the one that captures popular imagination, is going back, traveling into the past. That's where paradoxes arise, and where our understanding of physics is much less settled. Let's examine forward time travel more deeply, because that is the kind we know is possible in principle. Special relativity and velocity time dilation. Einstein's special relativity demonstrates that as you move closer to the speed of light, time slows down for you relative to a stationary observer. This is called time dilation. In practical terms, if you hop on a spaceship traveling at 99.99% of the speed of light and then return to Earth, you might have aged a few years, while centuries or even millennia passed on Earth. For you, time has skipped forward relative to the world you left behind. This effect has been measured in particle accelerators and in precise clocks flown on airplanes. Thus, it's not speculative. Time dilation is real. However, there's a huge barrier. We cannot accelerate macroscopic objects or humans anywhere near the speed of light with current technology. Energy requirements become astronomical. But in theory, forward leaps are allowed by physics. Gravitational time dilation, general relativity. General relativity adds a twist. Gravity also warps time. The stronger the gravitational field, the slower time runs. If you were near a very massive object, say a neutron star or a black hole, time for you would run more slowly compared to someone far away. So if you orbit near a black hole for a bit and return, you'll find more time has passed elsewhere. That effect is central in many sci-fi stories, think Interstellar. It's also very real. GPS satellites have to correct for gravitational time dilation to keep accurate time. So gravity gives another mechanism to travel into the future relative to others. So forward time travel is deeply embedded in relativity. The real speculative wonder is going backwards. Let's dive deeper. Under general relativity, space-time can curve, bend, and warp. Einstein's field equations admit exotic solutions, ones that could, in principle, allow world lines that loop back in time. These are called closed timelike curves, CTCs. A timelike curve is a path through space-time that always stays within the light cone, meaning nothing travels faster than light locally. A closed timelike curve is a path that eventually returns to the same place and time. If such loops exist in our universe, then traveling along one means going back into your own past while respecting the local speed limit of light. The concept isn't just a novelty. many solutions to Einstein's equations admit such curves under exotic conditions. Some candidate ideas. Gödel's universe. In 1949, Kurt Gödel discovered a rotating universe solution to Einstein's equations that allows CTCs. In his universe, the notion of absolute past and future breaks down. Tipler cylinder. A massively long, infinitely dense rotating cylinder could twist space-time enough that close to its surface, time loops form, but it requires infinite length or unrealistic densities. Traversable wormholes. Wormholes are tunnels connecting distant points in space-time. If you could manipulate wormholes, say, by accelerating one mouth or placing it in a strong gravitational field, you might generate time differences and effectively travel back. Conical singularities. A newer model suggests a conical singularity could allow a type of time loop in simple spacetimes. But these are extremely speculative, require exotic matter, negative energy, and may be forbidden by quantum effects or instability. One elegant way of thinking, spacetime might behave such that causality, cause before effect, is preserved, even if geometry allows loops. That brings us to paradoxes and consistency constraints. If backward time travel were possible, paradoxes loom. The most famous is the grandfather paradox. You travel back and prevent your grandfather from meeting your grandmother, meaning you would never have been born to travel back in time in the first place. Other paradoxes include bootstrap paradox, causal loops. An object or information is self-originating in time. E.g., you travel back and give Shakespeare his plays. Shakespeare publishes them. You learn them and go back to give them to him. No origin. Information paradox. Similar loop. Where did the information originate? To deal with this, physicists have proposed various consistency rules. Novikov self-consistency principle. This principle, proposed by Igor Novikov in the 1980s, suggests that in any timeline where time travel is possible, events must be self-consistent. You cannot change anything that would lead to a paradox. Any actions you take in the past were already part of history. Thus, paradoxes are simply prevented by the structure of physics. So you could travel back, but you could never kill your grandfather because history prevents it. Chronology protection conjecture, Stephen Hawking. Hawking speculated that physical laws, probably quantum gravity effects, will forbid time loops from forming. He called this the chronology protection conjecture. The idea is nature doesn't allow time machines. When conditions approach them, something breaks. Massive energy fluctuations, interstellar. This is not yet proven. Recent work, Tober and Costa. In a recent peer-reviewed study, Germain Tober and Fabio Costa proposed a framework in which closed timelike curves exist without logical contradictions. They present reversible dynamics consistent with free local operations, meaning you can travel in time without paradoxes. They show that even with multiple regions in spacetime, there are consistent processes that respect causality globally. In essence, under certain models, paradox-free time travel might be mathematically possible. Also, a study by Lorenzo Gavasino suggests that quantum mechanics itself might prevent you from altering the past. Memory and entropy would reset in loops such that paradoxical changes are erased. Thus, paradoxes are not fatal to the notion of time travel. Some models elegantly sidestep them via internal consistency. While macro-scale time machines are speculative, quantum physics offers intriguing glimpses of time control at the microscopic level. Reversing quantum states. In recent experiments, physicists have manipulated single photons or quantum bits in such a way as to reverse their states, effectively rewinding their time evolution. For instance, researchers at the Austrian Academy of Sciences and the University of Vienna used a quantum switch to revert a photon's state back to an earlier state. This is not time travel in the sci-fi sense, but a time reversal of quantum evolution. Quantum sensors that probe the past astray. A new kind of quantum sensor, based on entanglement, has been designed to perform detections that seemingly reach back into past states. The researchers likened this to sending a telescope back in time to capture a shooting star you missed. Such sensors don't transport you or macroscopic objects. They only exploit quantum correlations to infer earlier conditions. But they hint at a deeper structure to time in quantum mechanics. Closed timelike curves in quantum models. Physicists have even simulated closed timelike curves, CTCs, in quantum information experiments. For instance, Ringbauer et al. Carried out an experimental simulation of a qubit interacting with a past version of itself, modeling the nonlinear behavior and peculiar effects of time loops. These simulations point out how quantum dynamics might adapt or change in the presence of time loops, potentially offering clues about how a quantum theory of gravity might behave. So while we're far from sending humans through time, quantum physics shows that reversible time operations are physically meaningful, at least at tiny scales. Even if physics doesn't completely rule out time travel, enormous obstacles stand in the way. Exotic matter and negative energy. Many proposed time travel schemes require exotic matter with negative energy density or negative mass to hold open wormholes or stabilize spacetime, but no known material has those properties in usable quantities, and quantum field theory suggests negative energy must be constrained by quantum inequalities. Unimaginable energy demands. To warp spacetime, you need incredible energy. Manipulating wormholes or rotating massive objects to CTC thresholds would require energy beyond astrophysical scales. Stability and quantum back reaction. Even if a wormhole or time loop were created, quantum fluctuations, vacuum energy, and feedback back reaction might destabilize the structure and destroy it. The geometry may collapse before anything passes through. Quantum gravity unknowns. We don't yet have a full theory of quantum gravity, merging Einstein with quantum mechanics. It's possible that quantum gravity will forbid time loops outright, or that space-time becomes discrete or causally ordered at small scales. The chronology protection conjecture could emerge naturally from the ultimate theory. Causality and consistency constraints. Even in self-consistent models, constraints might severely limit what you can do in the past. You might only be able to observe events, not alter them in meaningful ways. Time travel tourism? Stephen Hawking once hosted a time traveler's party. He sent out invitations after the fact, hoping any time travelers would attend, and none showed up. He quipped, "The best evidence we have that time travel is not possible and never will be is that we have not been invaded by hordes of tourists from the future." If time travel were possible and widespread, we might expect visitors from the future or artifacts in our historical record, yet we see none. After exploring relativity, wormholes, loops, paradoxes, quantum mechanics, and energy constraints, here's where we stand. Forward time travel? Yes, in principle, and in practice for the future, via velocity and gravity. We are all moving forward in time, and relativity lets us skip ahead under extreme conditions. Backward time travel? It's not ruled out in all models, but requires exotic conditions, energy, and likely new physics. Even if it exists, causal consistency, quantum constraints, and stability issues may render it effectively impossible for macroscopic beings, or only allow observation, not intervention. In summary, time travel remains speculative for the past. Some models show paradox-free loops, quantum tricks show partial reversals, and the theoretical pathways exist, but the practical, engineering, and physical barriers are colossal. Science fiction gives us fantastical machines and dramatic stories. Reality gives us the strict laws of physics, which may allow some versions of time travel, but only under extreme, exotic, and yet undiscovered conditions. Let's imagine, if a time machine existed, how would a journey play out? You might emerge in a looped region where space-time points overlap. You might not be able to change anything, Novikov style, just observe. Crossing the threshold, the chronology horizon, might subject you to unimaginable gravitational or quantum forces. Your memory and entropy might reset or be curtailed in such loops. The machine might violate energy conditions, collapse, or evaporate before use. From a practical standpoint, Any time machine would likely require advanced control over gravitational fields, space-time geometry, quantum vacuum fluctuations, technologies far beyond our current grasp. Yet exploring these ideas fuels our drive to unify physics, to find quantum gravity, and to probe the boundaries of causality, information, and existence. Let's glance at recent developments and where the frontier lies. Paradox-free time travel models by Tobar and Costa show mathematically that non-contradictory closed time curves may exist. Quantum memory reset loops. Gavasino's work suggests that memory and entropy constraints might prevent altering the past, effectively shielding causality. Conical singularity model in space-time geometry offers a simpler framework allowing time loops. Quantum experiments reversing time. Scientists have reversed states of photons and qubits, flirting with time reversal in the lab. Quantum sensors probing past events. Via entanglement, some detections appear to go backward in time. Two-time dimensions theories propose that adding a second dimension of time could reconcile quantum non-locality and relativity. These are still early-stage speculative ideas. None approach the scale required to send humans through time, but the future may reveal deeper structure to time itself. So, can time travel ever be possible? The answer is, for future leaps, very likely yes, and it already happens in a limited sense. For traveling to the past, maybe. Some models permit it, but only with exotic conditions and subject to strict consistency constraints. In practice, huge barriers remain: energy, stability, quantum gravity, paradox resolution. Time travel remains one of the greatest frontiers at the intersection of physics, philosophy, and imagination. As we deepen our understanding of quantum gravity, of space-time, of information, perhaps someday we will unlock whether time's arrow is absolute or bendable. In the meantime, we can travel in time with our telescopes, looking billions of years into the past, with clocks, moving forward faster, and with our dreams and stories. But hopping into a DeLorean and dialing October 13th, 1850 might stay in the realm of fiction for many centuries more. Thank you for joining this deep dive into one of science's most tantalizing questions. If you enjoyed this, feel free to like, subscribe, and hit the bell so you don't miss our next cosmic adventure. And let me know in the comments, would you dare travel back to the 19th century? Or perhaps visit the year 3000? Until then, keep wondering, keep asking, and I'll see you in the next video on Amazing World Facts.